All right, we'll get started here. All right, remember, if you need one of these, they're right down here. Or forget, I know my lab group, I did one of them did yeah. It's good. I around, did a good job. Now, all great news. That is not for sharing any answers on any quizzes. Remember, when an instructor goes into Canvas Analytics, you know when you log in, you know what question you were on, you know when you log out of the thing and went on Google or some other website. Just switch what number you log back in on, you know exactly how many seconds. The student last semester, I don't know if I told this class this, that you get some questions. Draw a balance penalty, for all the grams, multiple grams, with all the math in 4 seconds, but you never cheat. So, group chat's good. I hope you get a group chat going with the people around you for this class, or the people in your row or something like that. Communicate with people, that's good. But remember, it's not for sharing stuff on quizzes and things like that. Okay, speaking of quizzes now, this is the take-home quiz, right? So this is out there. I got 2 emails of people that couldn't print this, but I loaded it today. It loaded up fine in the Word. So the printing then is on, call the UWEC help desk. Do you guys have that number in your phone? I've seen some blanks. Your phone's up. There's the IT help desk. Oh, last night, here it is. Oops. No, it's calling it, sorry. There's the IT help desk. Put that in your phone. So if you can't print, if you got a Word doc sitting there, it should print. So if it can't print, call this number. Good. The lab printer was acting up last night, so I called it up. Okay, so after lab, let me make a couple comments about lab. Now, general comments. First of all, we saw this, and if you haven't had lab, you've got lab coming up. It was the length, the width, and the height with a centimeter ruler, which there should be 2 decimal places on a centimeter ruler. So I saw something like this. The length was over 10, so we saw like 14.81 centimeters, which is fine. We saw a width that was over 10, so that was 10 let's say 86 centimeters. 4 sig figs, right? Then I saw this. This was a single digit, 4.86, and no matter what, the student wanted 4 sig figs, and I saw this. You can't add numbers to a measuring device. It's got to stay the same, so you don't want to add anything there. Okay, so then when this calculates out in your lab, it's 3 sig figs going forward with everything to match that. So when you did the volume of this, your volume answer should have 3 sig figs because it's the same as the least. Then I saw this type of thing. How many sig figs for this number? This is 2. This 0 doesn't count. Because if you put that, remember, if you put in scientific notation, this is junk, right? So this is 2 sig figs. How many sig figs here?
3. This won't count. This won't count. This 0 is written there for a reason. Otherwise, they wouldn't write it down. So this says 3. How many here? 2. This 1's place does not count. This says 2 sig figs. How many here? 3. Now, this is a way, if you wanted the 10's place to be significant and count, you'd put the arrow under the 10's place, right? And this would be 2 sig figs. Here, this is telling us that we're good to the 1's place for both of these ways to do it, either a decimal point or a line over it. Okay, if we do the math with this is an addition problem. So even though this has how many sig figs? This has 4 sig figs, right? 4 here and 4 here. Your answer can have more than 4 sig figs in it for addition and subtraction because you're going with the least number of decimal places. The least number of decimal places. So this looks like it has 3 decimal places. So we're going to add, this is not a good example I threw up here. What do we get for this? What do we got here? 541, 7.541. All right, 7.541. And in this one, when you're multiplying or dividing, your answer is going to have the same as the least, right? So this has 2 sig figs. This has 5 sig figs. So we've got 7.2 times 819.61. So this comes out to be 5901.192. And we're going to cut this off at 2 sig figs coming in from left to right. We're going to report an answer of 5,900. Okay. One more thing from lab yesterday. You have to do, it gives you a stated grams. I want to say it's like this, 8.942. It might even be like this, grams. And I think you got to go to ounces. It says 5 sig figs, right? Okay. Now, try to use the same conversions now. Listen, I'm starting to see stuff like this. I see, this is what you do not want to do, first of all. And then I see some number up here, 1. And I walk up to the lab person, I say, is this 454 chickens, pigs, or cows? That's my question. The chickens, pigs, or cows? I don't know. Look what it is in there. Now this is grams to a pound. This is what you do not want to do. 99 times out of 100, if you start with 5 sig figs, you should end with 5 sig figs in your final calculation. This conversion just cuts you down to 3 sig figs. So you have to use 453.5924 grams. Make sure you're extending that up. Don't let your conversion cut your sig figs down. Does that make sense? Because this has 5 sig figs. This one right here has 7, right? So you're still good. Then it was something like this. 1 pound is 16 ounces. Now you might say, what about this? But this is exact. This would be 1.000000 pounds equals 16.0000 ounces. So this is one where you can get in trouble here. So this would be good. You can now have an answer that should have 5 sig figs. If you use 454, not so good. Does that make sense? Okay, so just some lab comments there. Okay. Any questions at this point? Questions. Let's review the format of the class. We're going to be going through what I call learning guides, right? Put it away class, or you're going to do on every chapter. Every chapter, we're going to take one quiz, and then we have how to go along with it, right? Now, owl, you do not need a code from me. You need to put the code in and then go in directly into Canvas, and it should work. And somebody can yell at me and say, you don't know what you're talking about, I'm fine with that. But if I click home here, you know what, I'm not sharing the screen right now, so I get you. Down here at week 1. If you go through right here, this is week 1. If you enter OWL right here, it'll automatically load. You don't need an instructor key. But you do need your code when you buy OWL, right? And if you go through that, it should work. Is this working? Vertical or vertical maps? See how it works. Okay, good. All right. Now, what do you got for questions? I don't care if you're helping out with everybody in the take-home quizzes. That's one you learn. Once you enter your answers, you're not sharing the answers, right? So I'll group quizzes. Right. All right, any questions? All right, yes. Oh, you can open up OWL. I recommend you can get into OWL at any time. Just look at it, see if you know how to do it. If it relates. So the OWL, you get so many tries anyway. You can pop up with questions. But you can look in OWL and go in OWL there a lot of times. Okay, anything else? All right, we're going to continue on here. So last time we really just kind of did scientific notation and sig figs so that we could get there in lab. So next week's lab is on density. You should be pretty good to get to density. We'll probably do it next Tuesday, but that's fine. Okay. Remember I said I'd almost do a miniature textbook because people don't look at their textbook anyway. So my summary, I grabbed stuff from the textbook. I grabbed stuff online of the stuff that I think is the best. And this is something that I just kept, I don't know. So let's look at this. Units of measurement. Well, we know that even for measurement and conversions, we even had some stuff about measuring in the Bible from way back and questioning whether or not people are honest, huh? Especially 200 years ago, you're going to buy gold from somebody, right? They're just going to throw a digital balance out there and here's an ounce for sure. This is a fair ounce, right? No, they're going to bring some kind of teeter-totter balance system that they probably cheated on, right? Okay. Otherwise, some early measuring. Cubit. Digits, width of a finger. Cubit, the length from the tip of the elbow to the tip of the middle finger. Paces and things like that. We call our system the English system, right? And our English system is from British, right? Now, even the British were smart enough to adopt the metric system and get rid of their own system in about 1965. How many countries are still using the metric or the English system? I'm missing a page here. I know the answer to that. I do not see it. What did I do? It's the United States, Myanmar, and Liberia. Don't take that off. I guess that took that off. Oh, no, here it is. Sorry. Here's still who's using the English system, huh? That's it. Everybody else metric. So when I was a kid, kindergarten, first grade, the teacher said, we're going to switch, US is going to switch over to the metric system. One time during chemistry class, I called my dad. He's 83 years old in Florida. Picked up the phone. I said, Dad, when you're in elementary school, did they say that you're going to switch over to the metric system? He says, yep. They don't even say that anymore. They don't even say it anymore. It's kind of sad. We'll talk about that more later. Obviously, if you go to Canada, if you've ever been to Canada, you're going to buy your gas in liters, your potato chips in grams, your Coca-Colas in milliliters. And the speed limits are in kilometers per hour. Okay, now we need this standard system. And this is a good comparison. There's 26 letters in the English alphabet. Yet these 26 letters, it is possible to construct all the words in the English language. Similarly, there are 7 letters in the language of measurement from which all units of measurement are derived. 7 letters are distance, mass, time, electric charge, temperature, amount, and luminous intensity. So if we go to the next page, or a page coming up here, it's these 7. 7 here are like the 26 letters of the English alphabet. These 7 will describe anything in the universe, any combination of these or these. So if you go down here, look at some crazy units here. You got capacitance. A farad is a coulomb squared times a second squared divided by a kilogram times a meter squared. But these are the 7 fundamental units: meters, kilograms, seconds, coulomb, electric charge. Temperature should be in Kelvin, capital K for Kelvin. Amount of substance, if you've taken a chemistry class, of course, you know that's mole. And luminous intensity is candela. And in the metric system, previous page, we have all these prefixes, right? Obviously, hopefully, something like mega and kilo seem familiar to you. Probably centi, milli, micro, some of those, right? Okay. Well, now, if you grew up in the metric system, this is the chart here is the same as the green. If you grew up in the metric system, you'd have a chart like this memorized from 3rd grade on. It would be really simple. All you have to do is move the decimal the same direction you need to go in this chart. So for example, if I have 1 gram to kilograms, now, sorry, the base unit is a single letter. So it might be a gram, might be a meter, might be a liter. It could be computer bytes. So it could be more than 1 letter, but typically in science, typically it's a single letter, right? Hard drives, terabytes, right? Terabyte hard drive, stuff like that, where this would be written out. But typically your base unit is going to be a single letter. So again, starting in 3rd grade, you would have this memorized. 1 gram, this would be your base unit. I want to go gram to kilogram. So on here, my base unit, if I start at my base and I got to go to kilo, same direction I go on here is to the left from 0 to 3. I'm just looking at my exponents here, 0 to 3, which means I'm going to move this decimal 3 to the left, right? So if I move it 3 to the left, I should get 0.001 kilograms for 1 gram. Yes. Megameters to meters. Megameters to meters. This is the base. Mega right here. If I start at mega, I got to go to the base. I need to go to the right 6 places. You're just looking at this exponent here, right? So if I take this decimal to the right 6 places, I should end up with million. Now, students mess up on this one. How many centimeters in a meter? 100. So we're going to move that decimal place only 2, not 3. So centi to the base is 10 to the minus 2. We're just looking at the absolute value of this to the minus 2 to 0. Starting at centi, we're going left 2. So we're going to end up at 0.01. All right. So this is really, really simple. Let me comment though, I need to add a number here. In fact, I'm going to do this for my next class. Number 16. I want, let's say 1 cubic centimeter to cubic meters. Now, forget about the cube. If I go centimeters right here to meters, I need to go to the left 2, correct? But since I have cubic units, I'm going to go left 2 3 times because I have cubic units. If I have square units, I would go twice, right? So my total here is I need to go to the left, 6 to the left, right? So you can use this chart. If I go 6 to the left, 1, 2, 3, 4, 5, and 1. You can use this same chart to do squares and cubes if you have areas and volumes. Same chart, if you stay within the metric system. If you're in the English system, grab yourself a drink. You're going to need it. Okay. Now, everything's fine and dandy in the US, even though Britain switched over about 1965. In the US in the 1980s, it was the automotive industry switched over to metric. And that was the US's first dose of metric. Right? And all your grandparents swore and hated metric wrenches and all that stuff. Okay, now, what if we need to convert in the English system? Let's talk about the English system when you were a kid. Let's do that a little bit here. Because in the English system, well, let's talk about, we got to back up. I want to give you one more example. Time out. I can show you another example of why we have to use things. Okay. Remember, I used the dinosaur example first, and I used the perimeter example where your calculator lies, right? You know your calculator lies. You know. Here's another one. Let me see if I can do this. This is my shirt gonna work. Oh yeah, we can do this. So if I go like this, yeah, that's not bad at all. I know I'm going to be tricky a little bit. How many milliliters? 275, 270, 275. I don't think we can get a 5 out of that. I think we can say 270, maybe to the tens place kind of, but we can't do the ones. I would call this probably 270. Let's call it 270. So do I have to flip my camera? Yes. All right. So 270 milliliters. Or again, zoom in. This might be harder. Oh, not bad. Hey, pretty good. 2.1. It's like 2.8 without looking at this closer, huh? 2.8. Let's just call it 2.8. All right, switch the camera. Plus, watch what I'm going to do. Here's my plus. Put that in there, right? Well, since I added that, plus 2.8 milliliters. So now you're going to tell me that there's 272.8 milliliters in there, right? No way, that does not work, correct? That does not work. Using the rules of sig figs, even though I added to it, what's my answer? It stays 270, right? It stays 270, even though we added it. Okay, so there's another example of sig figs and why we do sig figs. Now, in the metric system, it is so easy to grow up in the metric system. This paper clip is about 1 gram. If I have 1,000 of these, what do I have? Kilogram, right? If this is a meter, it is not a meter, but if there was a meter and if I had 1,000 of these, I would have a kilometer or kilometer, right? This volume right here is a liter. If I had 1,000 of these, I would have a kiloliter, right? If I take this gram and I chop it up into 1,000 pieces, I would have a milligram, right? If I take this meter and chop it up into 1,000 pieces, I would have that very, very small tick in here, which is a meter. If I took this liter, chopped it up into 1,000 individual pieces, I would have a milliliter, correct? Now, all those are based upon 1,000, or I could have 100 centiliters, 100 centigrams, but everything's based upon 10, correct? Everything's based upon 10. Now, here's what we do to our kids, maybe 2nd grade. We give them a ruler that looks like this. That we're going to measure in inches, class. And let's say that this is a 2 and this is a 3. Say, okay, class, what is the measurement of this right there? What's the answer? The first thing the teacher says is, okay, class, you got to figure out how many divisions there are in an inch. Right? How many divisions are there in my inch? 8, right? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 divisions in an inch, correct? So the answer to this is 3 inches, right? 3 inches looks a little off on the screen. 2 and 3 inches pretty close. Yeah, 2 and 3 inches, right? Now, 2nd grade. So we're going to make these connections. These little, and we can start to focus so full. This is good. 2nd grade, we're still making connections. I'll do this in this month. All right, I'll turn the air conditioning on. My daughter basically television. Air conditioning.
Oh. Well, that's more mean. Side by side once. Oh. These kids are making connections. So these kids are making connections. Okay, there's eight divisions in a hitch. What is the only connection they can make in the system with eight? What is what? 8 ounces in a cup, right? 8 ounces in a cup. Yes. Those kids are making that connection. Then you know the next connection they're making. It should be 8 inches in a foot, right? Then you know what we do next year to those kids? We blow their mind. We absolutely blow their mind. And we tell them, you know what, kids? Your teacher lied to you last year. There's an 8 divisions in an inch. We now give them this. We'll give them something like this. We actually blow their minds. You know what they're thinking? I don't know, if there's 16 divisions in that inch now? I'll count them out. How many? 1, 2, 3, 4. Yeah, there's 16 divisions in the inch now. In 3rd grade. You know? Does that mean now that there's 16 ounces in a cup instead of 8, right? I think you go 32 and 64, right? And 120 inches each. Right? Think about it. And then we tell them, okay, class, how many ounces in a cup? 8 ounces in a cup. How many cups in a quart? How many cups in a quart? 4, which makes how many ounces in a quart? 32, right? And how many ounces in a gallon? 128. Can they make any connections? Can they make any connections? How many inches in a yard? 36. Why do you go 32? Can we get one thing? Can we get one thing the same? How many? Well, 128 ounces. How many cups in a gallon? 16, right? How many ounces in a gallon? How many inches in a foot? Let me give them this graph. Okay, Johnny and Susie, we give them this graph. Before you go out for recess, your parents measured your closet, and one was 8 feet, 8 inches, and the width was 5 feet, 6 inches. Figure, add this up before you go out for recess. Okay, no problem, teacher. Let's see, 14, that's 4 inches, 9. 14 feet, 4 inches, teacher. I want to go out for recess. What's the teacher say? Sit your butt back down there. You're not going out for recess till you finish this problem. What's the teacher tell him? First of all, what did this smart student assume? 8 plus 6 is 14. That's 4 inches. Carry the 1, right? Assume there's 10 inches in a foot, correct? Who the hell would put 12 in a foot? That doesn't make any sense. What's the teacher tell him to do? Convert everything to inches, right? Then you convert everything to inches. So let's see, we got to multiply that by 12. That's 96. This is 104 inches. This is 60 inches. This is 66 inches. They get 170 inches, teacher. I'm going out for recess. Teacher tell him. Sit your butt back down and convert that back to feet and inches, right? Divided by 12, 170. We can go 1, that's 12, that's 50. If we go 50, we can go 4, that's 48, that's 2 left over, 14.2 feet. It's not right, is it? It's not 14.2 feet.
It's 14 and 2/12 of a foot, right? 2/12. I just tell you. Politician, get this measure over the metric system. It's child abuse. Last president had it on his desk was Bill Clinton's second term. And he didn't sign it. That was the last shot we had, converting this country to the metric system and getting rid of this child abuse. Because this is crazy. Nobody would do this to their kids. Except for in America, I guess. The most advanced country supposedly in the world, and we do child abuse to our kids when it comes to this. All right, let's continue with how the child abuse goes then. Because we've got all of this crap here, right? In the English system, 1 foot, 12 inches, 1 yard, 3 feet, 1 rod, 16.5 feet, 1 mile, 1,760 yards, 1 mile, 5,008 feet, 1 6. These really relate well, right? There's nothing here that relates to anything. It's just child abuse. Now, hopefully you've done some converting units. I type this out. I will do what I call a conversion H, so I will square these off. So we know that if you are going to do a conversion, for example, we have a 13/16 inch wrench is my example here. And 13/16 is 0.8125 inches. If I start out with inches, as long as I have the same unit in the numerator as and denominator the same, I can just cancel units, right? This looks familiar to you. You've done this somewhere. If you want, you could put this over 1. It's not going to matter. Now, make sure you're writing this in there. If you just have a 1 and 254, I'm going to ask you if it's a pigs, chickens, or cows. Make sure you write in what it is. Math-wise, we're just going to multiply these 3 numbers, right? We're just going to multiply those 3 numbers. It's 20.6 millimeters, so we really have to get a 21 millimeter wrench. In this example, I am doing, and what I would do is, and I do this, I'll just draw a line all the way through this. How many seconds are in 1.2 decades? Now, if you knew how many seconds were in a decade, you could do this in 1 step, right? We would have decades down there, seconds up there. Otherwise, so we got to use multiple steps. That's fine. Why the 0.25? Why the 0.25 days in a year? Leap year, right? Every 4 years. Again, you're going to cancel units till you end with the unit you want. It doesn't matter. Again, it doesn't matter how many steps. I had a problem like this yesterday in class, and it looked like this. It was 1.4 yards equals, don't write this down, blank inches. And I just walked around the room to see how many steps it took. Most did it in 2 steps. One student did this. You can do that, right? If you do it in 1 step, you're going to go 1 yard is 36 inches, right? But it doesn't matter how many steps you take. as long as you're putting true mathematical statements in this conversion H. I call it a conversion H. You are just putting true mathematical statements in here. All right, let's do this one down here. This is English to English. We can't just move the decimal. So let's write this out. 135 ounces. 5 ounces. How many ounces in a pound? 16. How many sig figs are we starting out with? 3. So if I have ounces here, I'm going to automatically put ounces down here, and that is 16 ounces in 1 pound. Is this going to limit my sig figs? No, because you can assume this is perfect. 16.0000 ounces, 1.0000 pounds. I can do this problem in 1 step. So I'm going to take my 135 divided by 16, grab your calculator. Your blood flows to your brain when your calculator is being used. Get more blood flow to the brain, use your calculator. So if I do this to 3 sig figs, I'm going to get 8.44 pounds. Yes? 8.44? Okay. $1.75 miles. Oh, the feet to miles. Some of you know. How many feet in a mile? 5,280. That's, another child abuse number, right? 5,280. Right, we got to get the yards. Now we need to go 3 feet in 1 yard. Miles will cancel out. Feet. Yards here. Grab your calculator. Your blood flow is better to the brain. You're staying awake better. You're staying more involved when you're using your calculator. Use it better than I did, though. Three sig figs, this actually comes out all right. 3080. Okay, so 3080 yards. That is 3 sig figs, right? This 0 doesn't count. Okay, that reminds me of an ugly owl problem I did not put in this learning guide yet, I don't think. I'm going to look here. There's an ugly owl problem. That's something like this. I can think of it. Oh, okay. Yeah. I think maybe it looks something like this. Say 9.1 minus 0.000016. Yes, it looks something like this. I call this an ugly owl. It looks something like this. You can do this fine. In the denominator though, what's the result when you subtract this in the denominator? Let's get 9.1, right? So there is an ugly owl question that looks like this, and this is really 862 minus 86 is fine. You're just going to divide by 9.1 because you have no business subtracting this number from 9.1 using the rule of the sig figs. I believe it's something like this. Come across it in the ugly owl, write it down for me, will you? Something like that. There's going to be one or two versions. Show it to me Tuesday. But it's something like this where you cannot subtract from the denominator. Okay, let's go to the next page. Now, previously we did area and volume in the metric system, and we can move the decimal point 2 times for area, 3 times for volume. And we'll get to that down here. But this example here gets us between the systems. So right here are some good conversions to write, maybe even on top of your green sheet because they're most common, or maybe we could highlight them, but maybe and put these on top of your green sheet. These are the most common, I would say the most common ones to get you between metric to English or English to metric, metric to English again, English to metric. These are the most common ones. So if you want to write these on top, maybe that's a good idea. I'm sure they're on the sheet here somewhere. I'm sure they're on here somewhere, but you'll glance at these a lot faster than if you just put them on top. But those are your common English to metrics. Okay. Now, we're converting 1.5 tons to grams. This, of course, is English. This is metric. So somewhere along the line, we got to use an English to metric conversion. I'm going to start out with 1.5 tons. Tons to pounds. And then this is the conversion from English to metric. Now, I messed up on my sig figs. No, I didn't. That's right. 3 sig figs here to start out, 1.50. This 0 is significant, right? This 0 is significant. 3/6 times 10 to the 6 grams. Okay. Again, previously we did a problem where we converted within the metric system. If you have square units within the metric system, just move it twice. If you have cubic units, move it 3 times. In this child abuse system, it doesn't work that way. First of all, if this is 1 foot and this is 1 foot, how many square feet? 1. If I convert this to 12 inches, how many square inches in a square foot? 144, right? And you could do that. You can go 12 this way, 12 this way. right? And you should end up with 144 squares in there. So we know that 1 square foot is equal to 144 square inches. Some of you can remember that child abuse number. I don't know. What if we went to cubic inches? What if I now stretch this to a cubic inch or cubic foot? 1 cubic foot is how many cubic inches? You know what that number is? 1728. Another child abuse number. We're going to stay away from those numbers. We're not even going to do it that way. Okay? We don't need to do it that way. I'm going to do it within the metrics English system first. Let's say that I'm going to do the problem right here. Let's say we've got, I don't know. We'll use 1.6 times 10 to the 8th. Let's say cubic inches. I'm going to convert this to cubic miles. Oh, this is child. Oh, man. But now, let me show you this first way first. I want to get feet first. 12 inches, 1 foot. Now, there's a couple ways to do this. I'm going to write small. You can go 12 inches, 1 foot, and you could do that 3 times. Maybe you've been taught this way. Watch this, right? That would work, correct? Math-wise, I'm going to take this number, I'm going to divide by 12, divide by 12, divide by 12, right? The other way to do that is just to put it in parentheses. So now I'm going to do it in parentheses. Now I want cubic miles. So I'm going to go 5,280 feet. 1 mile. But I'm going to cube this. So I can put a cube like this. Cube like this. That would get me to cubic miles, right? But in my calculator, I'm going to take 1.6 to the 8th, divide by 12, divide by 12, divide by 12. I can divide by 12 rather than try to do the cube button or something like that. I'm going to divide by 5283 times. In fact, I'm going to do that right now and see what we get. 1.6 to the 8th. Ooh, I messed up at the very end. I just put 580 instead of 5280. So I'm going to do times 580. And now I'm going to divide by 5280. That'll work. Ready to get this? 6.3 to the minus 7. All right. So this comes out to be 6.3 times 10 to the minus 7. Cubic miles. Huh? Wow, that's just child abuse. Okay, if we have to use square, and you do this in lab, I think you do square centimeters to square feet, maybe like this or something. So if we want to convert square feet to square centimeters, (1 foot, 12 inches). But since we have square units, we're gonna square, right? Top and bottom. And then we got to go English to metric, 1 inch, 2.54 centimeters. This is how you'd put this in. This is the fastest calculator solution right here. That should get us 232. 3 sig figs there. Now remember, these zeros do not count for sig figs. This 0 counts. And you're really saying, well, that 0 must count, or the person went to wrote it down, right? Okay, in the next one, we're doing cubic millimeters to cubic feet. Cubic millimeters to cubic feet. So there's 10 millimeters in a centimeter, but we're going to cube it. Then 2.5 centimeters in 1 inch. 12 inches in a foot. Math-wise, divide by 10 3 times. You're going to divide by 2.54 3 times. And then divide by 12 3 times. Fastest way to do it. Okay. See if we want to do. I think we can do it. 18. We'll do 18. We'll start out with 1.2 cubic yards. Let's go yards directly to inches. We're going to go 1 yard is 36 inches. Since I have cubic units, I'm going to cube this. I'm going to cube this. I'm going 1 inch is 2.54 centimeters and all right, I'll let you punch that in. The answers are at the bottom. We're doing 25 feet per second to miles per hour, 25 feet per second. Now, if you want, it's really 1 second, but we don't write in the 1. Now, we need to get seconds to hours and feet to miles. Right? Steps this takes. It can look ugly, ugly, ugly. I want to end up with miles on top and hours on the bottom. It doesn't matter what it looks like. Let's go directly to hours. I want to cancel out seconds right here, right? Seconds to hours. How many seconds in an hour? 3,600, right? 60 minutes in an hour and 60 seconds in a minute. This number here is 3,600. Notice seconds cancel out, right? Now I'm going to cancel out feet and I'm going to put it down here. That is 5,280 feet in 2 cancel out. And I have the unit I want in miles per hour, right? All right. Number 20. World record marathon, 2 hours, 1 minute, 39 seconds. I qualified for Boston, but I didn't run it that fast. And you might say, oh, I don't know, big fat area, I don't know. So what? You can't relate to that until you break down the units. What's the distance of a marathon? 26.2 miles. Okay. Now let's do minutes per mile. Let's make this 120 minutes, right? 120 minutes, another minute there. So this is 121.39 is going to be about 2/3. 39 divided by 60. 65. 121.65 minutes. 26.2 miles. So if I take that and divide it out, I get 4.6431 minutes per mile. So you know now they're running under a 5-minute mile for over 2 hours for 26. Now you can relate a little bit, right? Now let's take this leftovers right here. So I have this in my calculator. I'm going to subtract the 4 out. That's my leftover minutes. 1 minute is 60 seconds. So I'm going to multiply this by 60. And I get 38.6 seconds. Let's call it 39 seconds. So their pace is 4 minutes. The world record pace, 4 minutes and 39 seconds per mile for running over 2 hours long for 26.2 miles. That is craziness, right? Now you realize when you break it down into something you can relate to, because I'm sure your mile time was this good, right? Just for a mile, you only had to run for, 6-7 minutes. They're running at 4:39 pace. To break the world record or to get under 2 hours, when I calculated it, it's not a lot. They got to get down to 4:36. 3 would be 4:36, right around 4:36, 4:35. Okay. Let's talk about accuracy versus precision. There'll be a question on the test for sure on this. Now, right here, this looks good. You're accurate and you're precise, but let's compare these two. This example right here have good precision, right? You're just not accurate. Now, this could happen to you in the chemistry lab. And there's an experiment you have to do. If you don't get within 5%, you have to do it over. And it's kind of a pain to do it over. And some people have to do it over 4 or 5 times. Well, it'd be an example of you do an experiment 3 or 4 times and you're doing great work, right? You're getting the same wrong result multiple times. So your technique must be good. There's just one flaw. What would be an example of a chemistry lab where you're not getting the right result, but you're getting the wrong answer consistently? What could be a problem in the lab? Graduated cylinder wrong every time and misinterpreting that. You could go over to the balance and it wasn't tiered to 0, right? So use the same balance, which started out at -5 or something like that, right? The balance could be off or not calibrated. So there is an example where you could end up like this. So this is good precision, not good accuracy. I don't know. I think the phrase SOL kind of comes to mind on that one, huh? All right. Let's talk about some beginning stuff here then. On page 11, we're going to end up with density here. Yes, for next time. We're going to finish up. We won't get through density today. Okay. So I actually started filling this in. So the study of the composition, properties, and interactions of matter. And we know the path of discovery that leads from question and observations to law or hypothesis to theory, combined with experimental verification of the hypothesis and any necessary modifications of the theory, scientific method. I'm sure you've used the scientific method many times. You just maybe didn't know it. It might be as simple as, I don't know if you old farts remember a CD player. Yeah, a CD player. You ever use a CD player? So if the CD skips, CD is skipping. How do you know if it's the player or the CD? Put a new one in, just buy another one, right? Toss that one. What if that one skips again? You just wasted your money. You just throw that one in a different CD player, right? Get on your group chat. Hey, who's got a CD player? Right? You get on your group chat. Oh, I got one. So you put it in there and that one skips again. So you know it's your CD, right? Or you get on your group chat and say, hey, who's got a really nice CD? I can test it out. They put theirs in and it doesn't skip. Then it's the CD player, right? So I'm sure you guys have used the scientific method many times. Okay. We do a lab after density. I'm not sure why, but I'm just following orders. And we do the gas laws, but we don't cover it in lecture. So, but we talk about kinetic molecular theory of matter, helps us interpret the properties of solids, liquids, and gases. Anything that occupies space and has mass, matter. Definite shape and volume, solid. A fixed volume takes the shape of the container, liquid. I can pour this water into a square beaker. Doesn't matter what shape of the container, correct? This liquid is going to take the shape of the container. Takes both the shape and volume of the container is a gas. A gas is going to fill up the container no matter what. Now let's talk about mass versus weight. Versus weight. If you step on a bathroom scale, how's that scale? So if here is the bathroom scale. Step on the bathroom scale like this. And I look at the numbers. How's it work? Gravity. Right? Gravity is the pushing you to the scale down there. It still work. Swimming boy and water. Where's the kind of pull? Now I take my bathroom scale and I'm standing on to the moon. Is it gonna work? That's absolutely right. It work.
What's the number gonna be? Oh, somebody ever asked you how much you weigh? Divided by 6. They didn't mention you. Divided by 6. So if you weigh 120 here, you're going to 20 pounds on the moon. You're 180, you're going to weigh 30 pounds. Because the mass of the moon is 1/6 as much, right? So when we do weight, you're really measuring how much gravity is pulling. So if you get away from the center of the Earth, you get higher up. You get Denver, Colorado. After you have less air, right? You have high altitude bathing instructions and cooking instructions and things like that. So we know that weight is going to change. So in the chemistry lab, we have to do mass. So somewhere along the line, somebody said, hey, this is going to be a standard kilogram forever. And that's what we have done. There is a standard kilogram in a vault in Switzerland, I think it is. Copied it. Now, on Earth, if I wanted to mass out this dog, I'd put 1 kilogram on there. Gravity's pulling on this side and gravity's pulling on this side, no problem. If I go to the moon, gravity's still pulling, gravity's still pulling. I would still have to put 1 kilogram on there on the moon, right? It's going to take 1 kilogram to balance it. It's still going to have to balance, and this is a standard 1 kilogram. This dog has a mass of 1 kilogram on Earth and 1 kilogram on Earth. We are always comparing to a known mass. So now, old way to do it in the chemistry lab is you had to use tweezers and you didn't want to touch any of these things to put oil on with your skin. And there was even smaller ones, and you had to keep adding these masses until you got your beaker to balance like this, and then you added them all up. It took forever. Now what do? We throw something on a digital balance. So these digital balances, these are calibration masses. Every time they're moved or shipped somewhere, the internal computer sets this to say this is 2,000 grams. We measure mass. How do we measure mass? All of our digital balances should have been calibrated with known standard masses. Now, let's talk about these types of matter. We have types of matter. We can have a pure substance or a mixture. Genius. Back to your little kid days, child abuse. You may have seen the word homogenized on your milk carton. Homogenized milk. They still do little milk cartons in school, right? Everybody got the little milk cartons. Kind of but it said homogenized milk. You still say homogenized milk? You remember seeing the word homogenized on there? Yeah. If they didn't homogenize milk, what would happen? It's going to separate, right? What's going to separate it? That's going to separate, right? And that's going to float to the top. I will give you, I will show you a video of that next time we meet to make sure we've got that all straight. Now, next time we meet, we'll cover density, and we may get to the next unit. We should, I hope. I've got quite a few videos next time. So don't bring popcorn, but it's close to bringing popcorn next time. There's quite a few videos. Print off the next chapter 2 that's out in Canvas. So either load it on your note thingy or print it, because we should get into chapter 2 next time we meet. All right, question. Anybody know where the attendance sheet is? It's right here.
You can always add to it next time. The agenda sheet, yes.
Yeah, you bring out table. That should be able to. Oh, you're gonna get your answer. So you mentioned, so there's 40. Potentially. But literally, it's in back.
It's gonna be like actually review next month.
There's a big chair.